Section 10.2, Simple Harmonic Motion in the reference circle. First, we're going to take a look at displacement and how that ties into our simple harmonic motion. A really nifty thing here is that the simple harmonic motion that we described for an object that is oscillating up and down, right, like on the end of a spring, turns out to be exactly the same as if we shine a light on an object that is traveling in a circle and look at its shadow. So here's like a shadow graph, right, where we shine lights on this blue ball that is spinning around the edge of the circle. And what it looks like on the screen, again, follows this sinusoidal motion. So we're going to describe that displacement x, the distance from the equilibrium position, as a, the amplitude, times cosine of theta, which we could also then calculate as a cosine omega t. Let's take a closer look at this. So if we look, instead of seeing this side view, if we look at a top view of the film, where we have this ball that's traveling around in a circle, then at any given point, the film shows us the displacement, the distance in x from its equilibrium point at x equals 0. So, you know, it starts out when it's stretched and it's at the full amplitude a. So for our circle, the radius of the circle is a. That's the largest of the amplitude we can ever get. As the ball rotates around, though, the shadow is just this x component. So if we want to relate the overall amplitude to x, if we know that angle theta, we can do that. We have a right triangle here. So once again, we can use some trig, and that's where cosine comes in. Cosine of theta is going to be adjacent x over hypotenuse a. Or in other words, x is equal to a times cosine of theta, as written over here. Now theta, we know, is our angular speed or angular velocity. And that we can write in terms of it, or theta, sorry, is angular displacement. We can write it in terms of our angular speed, right? We know angular speed, omega, is just equal to the angular displacement theta divided by the time. So instead of writing it in terms of the angle theta, we can fill this in as omega t, the angular speed times the time. So this is how we will know at any given instant the displacement of our spring. Anytime any object is in simple harmonic motion, the displacement is given by the amplitude times cosine of omega, the angular speed, times time. Now, before we continue, it would help to define some quantities here. So A is the amplitude, and that's the maximum displacement. That's the furthest away possible from the equilibrium position at 0 to all the way out to that maximum distance away, A. Period is something we've seen periodically. It's noted with a capital T, and it's the time it takes to complete one full cycle. So here, if we start our cycle out going from negative x to positive x, then we could go swing out one way, but this won't be a full cycle yet because we need to also catch the backswing, right? So one full cycle is noted on either side of this shaded region. And the time it takes is that period. Similar to period is frequency, and frequency is the number of cycles per second, which is often just referred to as hertz. Hertz is equal to inverse seconds. So the frequency is 1 over the period. They are the exact inverse of each other. Now, it turns out our angular speed can also be written as in terms of frequency. So omega is equal to 2 pi times our frequency, which is equal to 2 pi over t. And this is known as the angular speed or as the angular frequency. So those two things can be used interchangeably. But either way, it's going to have units of radians per second, as opposed to frequency is just 1 divided by seconds. So those are some important notes there, and those definitions will help us as we continue to define more quantities. Continuing on, after displacement, our next topic is going to be, well, it's going to be our velocity, right? So for velocity, we can once again look at this ball that's moving around in a circle, but now we're going to look at that tangential velocity, the direction of motion, and we're going to look at the shadow of its velocity, or the x component of that tangential velocity. To get the x component, you could show, I'm not going to expect you to derive this, but if you're interested, you could go and look into the details of this, but you could show that the x component of the velocity is negative times the tangential speed, the overall speed of the object, times sine of theta. Once again, for theta, we're going to plug in omega t, our angular frequency or angular speed times time. And this vt, we can relate to our amplitude, right? If we remember that our tangential speed, our tangential speed then is just going to be equal to the angular speed times the radius. So r times omega, and our radius here is just the amplitude times omega. So this gives, at any given instant in time, the velocity of our mass on the end of a spring, of our object that is traveling in simple harmonic motion. Note the negative sign does matter. That tells you the direction that it's moving in the velocity. We can also think about what's the very largest the velocity could ever be. And to figure that out, we need to figure out the largest value of sine. So sine of theta, or sine of omega t, is always going to go back and forth between -1 and 1. Those are the largest values that sine can take on. So that means our V max is going to occur when sine is equal to 1 or -1. In other words, it's going to be everything in front of the sine is our V max. So that's what this is trying to show here. That V max is just the amplitude of the motion times the angular speed or angular frequency. Let's look at an example of this in action. So the maximum speed of a loudspeaker diaphragm. So loudspeakers, if you've ever ripped the cover off one of them, there's actually a part that moves back and forth. It oscillates back and forth, and that's what generates the sound, is the oscillations. Super cool. Well, for a frequency of motion that's 1 kilohertz and an amplitude of 0.2 millimeters, what is the maximum speed of the diaphragm? Then we could also ask, where in the motion does this maximum speed occur? Well, the maximum speed of the diaphragm, we can look at our velocity equation, how velocity depends. At any given moment, the velocity is equal to negative amplitude times omega times sine omega t. But if we just want the maximum, all we need is the amplitude and the angular frequency. So V max is equal to amplitude times angular frequency. Note that they gave us the frequency in hertz, kilohertz to be exact, which is often what frequency is given in terms of. 1000 hertz is pretty mid-range, a little bit on the high end. A lot of times orchestras tune to 440, right? 440 hertz. So for this angular frequency, we're going to have to adjust to write it in terms of our normal frequency, right? So A times 2 pi times the regular frequency F. Now this is something we can calculate. We have the amplitude, which has been converted from millimeters into meters with this 10 to the minus 3 for the milli, times 2 times pi times 1 times 10 to the third kilo, prefix being 10 to the third hertz, and that comes out to 1.3 meters per second. That's pretty quick. So that for speaker has to be moving very rapidly. where's that maximum speed going to be? Well, if you just picture something that's going back and forth, at either end, when it changes direction, it has to briefly stop. So that's going to be the lowest amount of speed, right? The largest displacement, because you're furthest from the equilibrium point, and we'll even see in a moment the largest acceleration because you're changing direction. But where we get the largest speed is going to be right in the middle, right where it's had the speaker or the spring has had the most time to rip that object back to the equilibrium position. And then the object keeps going and starts to slow down, and then starts to speed up again until the equilibrium position, and then slow down again. And there's this continual oscillation, which we'll continue to explore in the next part of this section. We've seen velocity, or we've seen displacement. What else do we have to cover?